Choose Your Own Adventure Lab, the Slinky Falling. Objective, to determine how a stretched slinky falls by analyzing a video and comparing it to the computer simulation based on Newton's and Hooke's laws. The results. When a stretched slinky falls, the bottom stays still until the top of the spring gets to the relaxed length, and then the spring continues to fall altogether. The computer model is based on Newton's and Hooke's laws can show this motion. The physics. We'll be seeing Newton's laws in this form. The final velocity is equal to the initial velocity plus the net forces divided by the mass times the change in time. We'll also be seeing Hooke's law, which is that the force of a spring is equal to the negative spring constant times the stretch, where stretched is equal to the length of the spring minus the relaxed length. Here we have our system, which is a stretched slinky falling in the negative y direction. The forces on the spring, or slinky. At the top, we have the force of gravity, which is the mass at the top of the spring times g. On the bottom, we have the tension due to the Hooke's law, which is the spring, which is equal to the spring constant times the stretch. And then we also have the force of gravity, which is equal to mg. Here's our video. The video was downloaded into Tracker and analyzed. The film was taken at 300 frames per second, so that information needed to be put into Tracker. The calibration stick was set to 0.065 meters, the relaxed length of a slinky, and the origin was placed at the top of the spring just as it was dropped. The slinky was stretched and it fell in the negative y direction. The data from that was then analyzed using Google Drive, and you can see in blue is the top of the spring, and it obviously is falling at a rather steady rate until it gets the relaxed length. And you can see the bottom just stays exactly where it is until the slinky gets the relaxed length, and then the top and bottom fall together. The model was based off of the Mass Spring Lab, and I just modified the program. So there is some stuff in here that is not really used by this program. I split the slinky into two kind of pieces, the top, which I did with a spring, or a helix in this case, and the bottom, which is represented by the ball. And so here we have our initialization codes, the ball mass, the spring mass, and I split up in different sections. I gave the bottom more mass just because it seemed like the coils kind of stuck together at the bottom. Then we have the ball's position, which is negative 0.683 meters, which was about half of what it was in the lab. I couldn't use the data from the lab because it just wouldn't all fit on the screen. And I don't know enough about VPython to make that work. Then we had the ball's velocity, which is 0, the spring's position, which is 0, 0, 0, and the spring's velocity again, which was 0. Some other initializations, our delta t was 1/410th of a second. It was so small because there were so many frames per second. G is 9.8, which is again the acceleration due to gravity, the spring constant. I got this offline. They said it was about 0.83 for a slinky. The relaxed length of a slinky was 0.063 meters. And then we just have the coding for the stretch of the spring and the L hat. Okay. Here's some further initializations. The kinetic energy and the potential energies I didn't really use because I didn't really need it for this one. That was from the last lab. The force of gravity was equal to the ball plus spring mass times negative 9.8. The force of the spring, again, was the negative spring constant times the stretch times L hat. The total net force, and that was only used for the bottom part of the spring, was the force of gravity plus the force of the spring. The next part is where you see Newton's laws. We've got the ball velocity is equal to the initial ball velocity plus the F net divided by the ball's mass times the change in time. For the spring, we have the initial spring velocity plus the force of gravity only divided by the spring's mass times the change in time. For the ball position, now it's updated to be ball position plus the ball's velocity times the delta t for both the spring and the ball. And that's really about it for the time loop. And here's the model running. And you can see pretty much the bottom stays the same and the top is falling. And then here's a comparison of the two graphs. And they're relatively close. Again, I couldn't plot them together because I couldn't get the data for the model to be big enough to match the data for the actual spring falling. The results. A stretched slinky falls from the top first. When the top of the slinky has fallen, then the entire slinky proceeds to fall to the ground. A computer model was made to show this motion, but a direct comparison was too hard for me to write with the coding. Some sources of error, I'm not sure if that KS was correct for the slinky. It did show the same motion, but again, the comparison was too hard because I didn't have enough knowledge of the coding.